Chapter 10, Migratory Insertion. A migratory insertion reaction is a reaction taking place in the around sphere of the metal M, where two ligands, one neutral and the second anionic, can couple together to form a new anionic ligand. For example, consider the metal M, metal hydride, and metal alkene. The hydride is a ligand anionic. Alkene is a ligand neutral. So H- can attack the alkene to generate a metal alkyl. So this is a new anionic ligand formed from the coupling of the two ligands. As we observe, the oxidation state of the metal M did not change, but the electron counting decreased by 2. The oxidation state of M in this example is M1, and in the metal alkyl formed, the oxidation state is M1. We have two ligands, each donor of 2 electrons, and here we have the coupling ligand, which is donor to 2 electrons. So the migration of H from M to another ligand will generate an empty orbital, and this empty orbital is very sensitive. The reaction of the migratory insertion is reversible. In direction 1, we have migratory insertion, and in direction 2, since we have a vacant site, so the alpha carbon elimination or the beta elimination is also possible. If the empty orbital generated by the migratory insertion reaction is not occupied by external ligand or by the solvent, so in this case we will favor the elimination reaction and the structure will return to the metal hydride alkene. If we want to compare, for example, the stability of the initial complex and that of the final, we know that the reaction in thermodynamics is favored when it passes from less stable state to the more stable state. The metal alkyl is a stable bond, but also in the initial complex we have metal hydride which can stabilize the complex. So one way to avoid the reaction in the opposite direction is to fill the empty orbital by another ligand, for example, phosphines, and this ligand is known as trapping ligand. We have two types of migratory insertion. The type 1, called 1-1 insertion, in which the metal and the X ligand end up bound to the same 1-1 atom. For example, we have MX anionic and we have CO. The CO ligand is donor to the metal M by carbon, since the carbon is less electronegative than oxygen. So the carbon has a partial charge delta plus, and in this case X will attack on the carbon and would not attack on the oxygen. So it attack on the same atom 1-1, and in this case the migratory insertion is 1-1 migratory insertion. The type 2 is the 1-2 insertion, in which the metal and the X ligand end up bound to adjacent atoms 1, 2 of an L-type ligand. For example, in this metal alkene, the X can attack on this atom of carbon or on the second. So we have 1, 2 migratory insertion, and X, if X is in the carbon 2 of the alkene. This is 1, 2 migratory insertion. In both types, the electronic counting decreased by 2, the coordination number decreased by 1, and no change in the oxidation state. The 1,1 migratory insertion is observed in case of carbonyl, and in case of alkene, we have the 1, 2 migratory insertion. So in the migratory insertion, no change in formal oxidation state. Example, in the case of the alkylidene that will be studied at the end of this chapter. The two groups then that can couple together must be in cis positions. So we open a vacant site by the migratory insertion. If this vacant site remains vacant, so the reaction would be favored in the opposite direction in the case of hydrogen elimination. So we use in general a trapping ligand like triphenylphosphine or other ligands to stop the back elimination reaction. The migratory insertion is in general favored on the metal centers poor in electrons. Consider, for example, metal carbonyl, and the metal M is poor in electron density. That means the carbonyl will give its maximum capacity to M, and the back donation from M to CO is practically impossible. So in this case, the carbon will have a partial charge delta plus, and X on the metal can attack carbon in this case easily. The anionic and the neutral ligands that can do migratory insertion with one another, anionic as hydride H-, alkyl, aryl Ar-, Sl-, oxo O2-, and the neutral as CO, alkenes, alkynes, and carbenes. The CO and alkyl migratory insertion is very important in organometallic chemistry since it's a source of the carbonyl. And in the carbonylation reaction or formation of or appearance of C double bond O in a molecule, the migratory insertion is the very important step. In this example of Mn complex, we have CH3- and the neutral ligand CO in cis position. The Mn is Mn1 and it's 18 electron complex. CH3- will attack CO to form MnCO-CH3, and we observe the appearance of the carbonyl function that can be generated, for example, by reductive elimination. In this complex, we have a vacant site. If this vacant site would not occupied, so the reaction will proceed in the backward direction in the direction of elimination. And in direction 1, This is migratory insertion in direction 2, we called decarbonylation. So to avoid the elimination reaction, we add the trapping ligand L and we form this complex. Hydride and CO migratory insertion to produce formyl is not common due to the non-stability in thermodynamics of the formyl metal bond. Some electronic effects of the migratory insertion. We have a complex of Fe and we have R and CO. R is anionic, so R will attack CO, or R will do, or CO will be inserted in the bond FeR, and we obtain FeCOR with the vacant site that is occupied by the trapping ligand. The acyl ligand formed is not as good as a donor compared to the starting alkyl. For example, we replace R- by COR, and R- is more donor than COR. So the first complex, by theory, would be more stable than the second. But the metal has gained an electron, or has replaced an electron withdrawing CO ligand with a better donating phosphine ligand L. This is true that R is more donor than COR, but L is more donor than CO, and CO, you know, that is a pi acceptor ligand, and L is a sigma donor ligand. So in total, we have two inverse effects. In the first complex, we have a ligand that is more donor than in the second complex, and in the second complex, the L ligand is more donor than CO. In total, we have a stability of the product formed, so the migratory insertion will proceed. As we said, when the metal center is poor in electron density, the carbon of the carbonyl bound to M is more electrophilic, so nucleophilic attack is favored from the more electron-rich alkyl group. Alkene insertion reaction. The insertion of coordinated alkenes into MH bond is very important reaction because it gives alkyl and constitute a key step in the catalytic reaction, including alkene polymerization, and this is one of the most important organometallic reaction. The polymerization reaction is known by Ziegler-Natta complexes. For example, zirconium alkyl and zirconium alkene complex. So we add alkene on zirconium and we obtain zirconium alkene. Then CH3 will do migratory insertion to the alkene and we form alkyl with the 3 carbon atoms, 1, 2, and 3. We add another alkene, so we have metal alkene and metal alkyl with the 3 atoms of carbon. We repeat the same reaction. This alkyl of 3 atoms of carbons will do migratory insertion to the alkene, and we will form a metal alkyl with 5 atoms of carbons, 1, 2, 3, 4, and 5. So we transform the first alkene to alkyl with 3 atoms of carbons. The 3 become 5. The 5 will become 7. The 7 by addition of alkene will form alkyl of 9 atoms of carbon, and it will continue. So we will have polymerization. As hapto-2 ligand, alkenes gave 1,2 insertion, and this is the reverse of the beta elimination reaction. Some insertion reactions are known to give agostic bonds, and we don't have, for example, metal alkyl, pure metal alkyl bond. And this is probably due or depend on the pathway for insertion into MH bond. The agostic bond will be studied in course of this chapter. The position of equilibrium in the direction 1, in the direction of the migratory insertion, or in the direction 2, in the direction of elimination, depends on the nature of the alkene used. If, for example, we have only metal alkene, the carbon of the alkene has electronegativity close to the hydrogen. So the positive charge on the carbon is not great, and the migratory insertion from X minus to the alkene will not be favored. If the alkene has groups which are electron withdrawing, like F, it will pump the electron density from carbon, and the carbon will have a pure charge delta plus. In this case, the migratory insertion X minus to this alkene C2F4 will be favored. Alkyne migratory insertion. Alkynes can do migratory insertion like alkene to produce vinyl groups as shown below. We have rhodium complex. We add alkene. This is a ligand addition, so we obtain rhodium alkyne. The H minus is anionic ligand, will do migratory insertion on the alkyne to open a pi bond, so we will obtain a metal with a group containing double bond. Why this reaction is called migratory insertion? The migratory insertion is two words. One, migration, and the second is insertion. There are two different directions that the migratory insertion can occur. Migration, when the anionic ligand moves and performs a nucleophilic attack or intramolecular attack on the electrophilic atom, in this case, for example, on the carbon. The insertion, when the neutral ligand moves and inserts in the bond M-alkyl, for example, and in the two cases, in the migration or in the insertion direction, we obtain practically the same product. So several experiments were done on complexes to know if the migratory insertion follow the direction migration or the direction insertion. So they found that most systems do migration, but both are possible in other systems. The following example shows a system where both are very similar in energy and the solvent used favor one or the other. In the Fe complex, we have in the direction of migration, ethyl migration to attack the carbon of CO, so we obtain FeCO, ethyl with opening of a vacant site. Then we can add a specific CO, carbon 13, and we obtain FeCO. In the direction of insertion, we use other solvent, so CO will be inserted in the bond Fe ethyl, so we open here a vacant site and we obtain FeCO ethyl. Then we add the specific CO and we obtain this structure. These two structures have different environment in the ligands around Fe. So we generally do not worry about the exact pathway. This is why we use the term migratory insertion to indicate that both directions are possible. And many organometallic complexes use the migratory insertion term, but they do not usually mean that they know what is the mechanism or what is the real mechanism or the real direction. Agostic CH to metal interaction known as the frozen migratory insertion. One can find an alkene hydride migratory insertion that does not go all the way. For example, in this complex of cobalt, we add H+, we obtain cobalt hydride, and cobalt, we have initially cobalt alkene. The hydride anionic and the alkene neutral are in cis position, so the hydride will do migratory insertion on alkene to form cobalt alkyl. And the alkyl has hydrogen in beta position, so the reaction will shift backward to form beta elimination reaction. In general, in some examples, we don't have a pure migratory insertion nor a pure beta hydride elimination. We have agostic CH bond, which is intermediate between the migratory insertion and the beta hydride elimination. In this complex, in this intermediate complex, the CH bond is not a pure bond, and the cobalt hydrogen is not a pure metal hydride bond. Normally, this is a transition state structure for a hydride alkene migratory insertion or a beta hydride elimination. Because the CH bond is sharing some of its sigma electron density with the metal, so the CH bond is weakened. In other words, the bond order of the CH bond is less than 1. The agostic bond CH can be observed by spectroscopic analysis. In infrared, μCH agostic is around 2,500 centimeter minus 1. In the normal CH bond, we have around 3,000 centimeter minus 1. In carbon 13 NMR, the normal is between 70 and 90 Hertz. The CH agostic bond is between 70 and 90 Hertz, and in the normal value it's around 150. This is the coupling of the CH bond. In hydrogen, the chemical shift for the agostic bond is between -10 and -15 ppm, so it's like a metal hydride resonance. Since the agostic bond is intermediate between the migratory insertion and the beta hydride elimination, so we have electronic and steric factor that can favor one of these directions. For example, if we use a specific ligand L, we favor the migratory insertion and we avoid the beta hydride elimination, and in this case, we could not observe the agostic CH bond. Carbene migratory insertion. Carbene or alkylidene ligands can also do migratory insertion with adjacent anionic ligands. In this example, we have M double bond CH2, so M carbene or alkylidene, and we have MX, and X is anionic. So X will attack on CH2 to open a vacant site, then the ligand L will occupy this vacant site and we have formation of MCH2X. If the X is hydrogen, so in direction 2, the reaction is alpha hydride elimination or alpha hydride abstractions. To note that in the metal carbene, we have a problem in the electronic counting. We know that the migratory insertion refer to the coupling of a neutral ligand and anionic ligand to produce a new anionic ligand. In this example, we couple the anion X- with the dianionic carbene to make a new monoionic ligand. So if we consider the carbene is 2- and X is 1-, so in this case the oxidation state of M is M3, and the product obtained by the migratory insertion reaction is M1, since L is neutral. So during this reaction, the oxidation state of M passes from 3 to 1, and this is a reductive coupling reaction, since the metal is being reduced and we are coupling together two ligands. To avoid this problem in the concept of the migratory insertion, we consider the carbene or the alkylidene as a neutral ligand. So in this case, we will have coupling of anionic ligand with a neutral ligand, and we respect the concept of the migratory insertion that states that we don't have a change in the oxidation state of M. Elimination of hydrogen. Elimination reactions, as we said, are the reverse of the migratory insertion reaction. We have several types of elimination. We can have a beta hydride elimination, or the elimination of hydrogen in beta position to the vacant site on M, and we form M hydride metal hydride alkene. So the beta hydride elimination is the inverse of the migratory insertion of H to alkene. We can have hydrogen in alpha position. So in this case, we form metal hydride carbene, and this is alpha hydride elimination. We have also elimination of carbonyl from the bond MC double bond OR to the vacant site, and we obtained MR MCO. This is known as decarbonylation reaction. So in the elimination, we don't have change in the formal oxidation state of the metal M. The elimination, the condition of the elimination, we should have a vacant site in cis position to the group doing an elimination reaction on. The 18 electron complex could not do elimination since it's saturated. So in this case, it has to be transformed from 18 electron complex to 16 electron complex to open a vacant site that can receive the hydride eliminated from the alkyl group. Other elimination examples. One of the hardest elimination reaction is the breaking of C sigma bond C. In this complex, we have metal alkyl and metal alkene bond. So the anionic CH3 will do migratory insertion to the alkene to form the metal alkyl. The CH3 group could not return to its initial place on M. So the reverse methyl elimination reaction is very difficult. Instead, we can have beta hydride elimination that can occupy this vacant site. But some organometallic experiments proved for some complexes that we have methyl elimination.